Alright, hello everyone. This is going to be the first video lecture. Probably going to have many more to come. This is a fairly improvised setup I have here. It's literally masking taped to the wall. So I guess grain of salt, and let's just jump right in. So this is for chapter 2.5. Yes, you can see that. Chapter 2.5, this is for function inverses. Everything I'm about to cover is already covered in the notes, which are posted to Blackboard. All I'm going to do is sort of give them voice and maybe a bit more explanation. So the concept of an inverse is you have a function which sort of takes one thing and sends it to another. And what we want to define an inverse function is, inverse is always denoted as raised to the minus 1. This is not to be confused with division, but regardless, we want the inverse of a function to basically reverse things. We want this to take sort of objects from the output of the other and give us the inputs of the other. So in a sense, an inverse function reverses what a given function has done. And so for f of x, f inverse of x sort of undoes f of x in whatever, undoing happens to mean. So if it's if f uses addition, it might use subtraction. If it uses multiplication, the inverse might use division, and some combination thereof. An easy example is if we have f of x equals 2x. And so by looking at this, we can sort of see what does it do to inputs. And this doubles the inputs, right? Fairly naturally, you plug in a number, it multiplies by 2, so it doubles it. And then we want our inverse function to do what exactly? Well, we want it to undo doubling. Undoing doubling is sort of the same as reducing it by half, rather than making it twice as big. And so this should be dividing everything by 2. And this, in fact, does reverse everything that the other function does, and so this is, in fact, the inverse of that function. I kind of just pulled this out of nowhere because it's really easy to see what the inverse for that one is going to be, but this next example is going to be slightly more involved, and we're going to be looking at Celsius to Fahrenheit. So we're going to come up with a function which converts temperatures in Celsius and sort of gives us what those would be comparably in Fahrenheit. There's a number of ways we can do this. However, since these are both linear functions, or rather the transition between them is a linear function, we can solve it the way we do normal linear functions. And to do that, we need to find its slope and at least one known point. You can find the slope from 2 points though. So let's just find 2 points that we know are going to be in this conversion and then sort of deduce everything else from there. So 2 points which we know are in this are at 0 degrees Celsius, being where water freezes. In Fahrenheit, that's 32 degrees. People can't see that, right? Yeah. And we also know that at 100 degrees Celsius, which is where water boils, comparably in Fahrenheit, water boils at 212. Also, as a sort of neat little factoid, negative 40 degrees Celsius happens to translate over into Fahrenheit also into negative 40. And so this is the only temperature at which both temperature scales agree. But that's a little, we don't need that. Here we have 2 points. And so if we are going to make a plot of this, I want to have my inputs be in Celsius. And so basically what I'm saying is the x-axis is going to be in Celsius. And the y-axis, being our outputs, are going to come out in Fahrenheit. And so the y-axis is going to be Fahrenheit. And I know that if we just sort of mark these out as 100 and 100, then 0 on the c-axis, in this case, the horizontal axis, is going to map to 32. So at 0C, it's going to output roughly here, which is 32 degrees Fahrenheit. And we also know that for the other point, at 100C, it's going to output to 212 Fahrenheit. And so that's going to be somewhere up there. And since it's a linear function, we can know for certain that this is going to be a straight line, should be a straight line connecting these 2 points. And so then every temperature that we want to find Celsius and Fahrenheit conversion for, we can use this line. Now, let's figure out the equation for this line. And the way we do that is we use these points and we sort of reorganize them into coordinate pairs, because this is the point 100, 212. And likewise, that's the point 0, 30. And so we have 0, 32, and we have 100, 212. And these are 2 points which we know lie on the line, so they uniquely determine the line, and we can use these to find the slope and intercept for an equation. We know that the slope of a line is going to be y2 minus y1 all over x2 minus x1. And in our case, y2 is the y value of the second point, so that's 212. Y1 is the y value of the first point, which is 32. And now we're doing the difference of the x terms, which x2 is 100 and x1 is 0. So we can use this now to solve for what the slope has to be. Doing this out, we get 212 minus 32 is 180, and 100 minus 0 is still 100. This can be reduced down to 9/5 in a number of different ways, but they all come out to 9/5. And so we now know that our slope is 9/5. A general thing in these video lectures is going to be, I'm going to move fairly quickly to conserve camera battery, memory on the memory stick I have in there, and so since it's a video, you can always pause it, go back. Hopefully you can zoom in a little bit too, rereading things, skipping ahead, whatever. So I'm not going to spend a lot of time. I'm also going to erase things pretty soon after I put them up, and that's just for ease of everyone. So we now know that the slope is 9/5, and now we just need to find the intercept so that we can write this in y equals mx plus b notation. We just found m. So we now know that this is going to be y equals 9/5 x plus b, and now to solve for b, all we have to do is use one of these 2 points and plug in the x and y values. I'm going to use the first one just because it's really easy. So in the first one, we would have 9/5 times the x value of the first point, which is 0, plus b, and we know that this is going to all equal the y value of the first point, which is 32. And so 9/5 times 0 is 0, so this whole thing goes away, and we are left with b equals 32. So now we can come back up to the beginning, and we can say we now know what m is, and we know what b is. And so we get the equation for that line, the one that converts between Celsius to Fahrenheit. Awesome. We can check our work a little bit just to make sure that everything's nice and sort of accurate. And we can do so by plugging in the other point, or we can plug in the more fun point of -40, -40. That's the one I'm going to do because that point wasn't used anywhere in the derivation of this formula, and so it shouldn't sort of vacuously give us back the right answer. In doing this, I'm going to say y equals 9/5 times -40 plus 32, and we are hoping to get an answer of -40 because that's how we will know that this equation is accurate, because Celsius and Fahrenheit actually do agree at -40. So, doing this out, we can see that -40, well, this can be rewritten as -8 times 5, and now we see that the 5 and the 5 cancel, and so we get 9 times -8 plus 32. We can simplify 9 times negative 8. That's going to be negative 72 plus 32, and that does in fact give us negative 40. So we've taken known points, found the slope, used one of those points to find the y-intercept, we found the equation, and then we checked that equation at a different known point, and it turns out to be correct. So this is in fact going to be a handy little conversion tool from Celsius to Fahrenheit. So I'll just write this over here. Also, since we have changed our x and y axes to be Celsius and Fahrenheit, when I write this, I'm going to write this as F equals 9/5 C plus 32, because our inputs are C and our outputs are F. Now, since we're talking about inverses of functions, you can probably see where this is going. We are now going to look for a function which does the opposite of this, or sort of undoes this. And that would be something which takes us from Fahrenheit to Celsius. And so we need to come up with an equation like how we did for this one, but which does it in the opposite direction. Oh shoot, can you see that with the glare? I'm not sure that's totally visible. Please tell me if this is not visible when I post this. Just in case, I will repeat it right here. Okay. Hopefully that is now totally in view. So now we are looking for something which takes an input in Fahrenheit and outputs in Celsius. And so one way we could find this different conversion tool is exactly the way we found the first one, by using known points, by finding a slope, by using that and a known point to find the intercept, and then we're done. Or we could ask a more sort of foundational question, which is, what is the relationship between a function and its inverse? Is it possible to find the inverse of a function given just that function? And so we have this equation, which gives us Fahrenheit from Celsius. Is there a way to use this to give us Celsius from Fahrenheit? And of course there is. The way we would do this is, effectively, we want to change which one is the input and which one is the output. And to do that, we can essentially solve for C in this equation. When we do that, we can see that to solve for C, we're going to end up with some equation where C equals something else, and that something else is going to have F buried in it somewhere. And so this thing that we get in the end is going to have F, we do something to it, and we get C. And so that's exactly what we want. We want a function which takes an input in Fahrenheit and outputs it in Celsius. And so by solving for C, we do in fact find the inverse of this function. Doing that really quickly, we subtract 32 from everything, which gives us F minus 32 equals 9/5 C. And then to get rid of the 9/5, we multiply by 5/9 on everything. 5/9, because everything cancels nicely, and we are left with 5 times F minus 32 all over 9 equals C. And so we have just solved our other function, and we solved for the opposite orientation of their variables, and now we have a different function. I'll rewrite it up here just so that I can erase it. So we have these two functions. And now, ideally, when I take this, which is also going to be the equation of a straight line, and plot it on exactly the same thing, maybe we will notice some kind of relationship between these two objects. And in fact, when we do this, we get something that looks like that, where this is now the point 32, 0, and somewhere over here would be the point 212, 100, sort of the exact opposite of what it was before. This equation takes an input in Fahrenheit and outputs it in Celsius, and this one does exactly the opposite. These are inverses of each other. And they don't do it simply by replacing the variables. Like, we didn't we didn't convert this by just literally swapping which one we called Celsius and Fahrenheit, because this no longer is going to be accurate because it's derived from a different property. So you don't swap the variables sort of in name alone. We actually have to manipulate the equation until they're in the opposite positions to each other. And that's what we did to find this. Another thing we can notice is this sense of it's the opposite in the graph can be more formalized when we notice that it is actually symmetric about the line y equals x. Y equals x, well, that's where inputs and outputs are the same, and so it kind of makes sense that if we are flipping which one we consider the input or the output, well, that would kind of make sense for them to be the same shape on the same graph, just sort of with f and c reversed. Where again, in this case, we're using the variables f and c. But in general, all inverses, so here let me actually write this. Here's an instance where backing up or going slower using the pause button is going to be helpful, because I'm going to move on. But we can say that all function inverse pairs are symmetric about the line y equals x. And again, this is because finding the inverse of a function basically is the same as using the same structure but to swap the position of the variables. And so it makes sense that the line y equals x should map to itself, and everything on one side of that line should map somewhere to the other side, and vice versa. So we get this very nice symmetry that allows us to, at a glance, determine about where the function inverse should drop out. So that was sort of a motivating example to give us this idea of what exactly